All right, so I think I've got it recording right now. What we're going to do is go through an example here, looking at the force on, or due to two charges here, Q1 and Q2. And they both have a charge of negative 50 microcoulombs, or excuse me, one has a charge of negative 50 microcoulombs, one of them has a charge of plus 50 microcoulombs. By the way, do y'all remember what the micro mean? Okay. Figured you would, but probably worth asking. All right. And what I want to do, what we want to do here is find the force at point A. Now we've got some distances here. The distance between these two is 52 centimeters. Point A is 30 centimeters above Q2. Which means it is 60 centimeters there. If we did the Pythagorean theorem, we would get that. All right. So before we even start any of the calculations, what you want to do is decide what's going to happen. Okay? And I think I said we're going to find the force. Actually, what we're going to find is the electric field. So, because there is no charge there at point A. It would work out the exact same way, or the process would be the exact same way if we were finding a force, except we've got a charge that's there. So before we even start doing calculations, tell me what you know about an electric field and which direction it might be going at that point and why. Okay, so remember when we were drawing the electric field lines? It goes positive to negative. So between the two, it would be going from here to here. But we're interested in this point up here. So what would be happening up there? Okay, so it goes from positive to negative, right? If we just had a single, what would the electric field look like up here? If we just had this one point, or one charge. Going out everywhere. So at point A, which direction would it be going? Huh? Up. Right. Okay. Now, so I'm going to put it in purple here for the electric field due to 2. It would be going up. Okay. If we didn't have charge 2, okay, straight towards, Okay, so that way, right? E due to 1 is that way. Are those the only two effects for the electric field shown here? Are the only two things here that are going to affect the electric field? Yes. Yes. Okay. So those are the only two things affecting the electric field. So we got a part, an effect that's pushing it that way, an effect that's pushing this way. If we have two vectors that are combined, which direction is your net electric field going to go? In between the two. Okay. Remember, there was two methods of graphically do it. You could do the tip to tail method. So I could put this one up here, or you can do the parallelogram. The net result is going to be an electric field going that way. Okay. You want to do that, go through this thinking process before you ever start trying to do the calculations. What's going to happen? Because you need to be able to describe it. Most of the free response questions are now descriptions of what's happening. And then at the end they'll throw in, okay, do the calculation. So from Q1 you have an electric field going this way. From Q2 you have an electric field going that way. The result of the two is a combination, something in the middle, going that way. Okay. So your net result is just that E going that way. They might give you something with forces doing the same type of thing. You got a force going this way, a force going that way. What's the result? Something right in the middle. Okay.
So how would we write like the words? The force. This is going that way.
What's it going to? Pointing towards Q1. That's exactly what I'd say. The electric field due to Q1 is going towards Q1 since it's a negative charge. The electric field due to Q2 is going away from Q2 because it's a positive charge. The electric field goes away. The net result is E, which would be in between the two. Okay. Again, that being able to describe it is pretty important. Just like when Ms. Ewing came in yesterday and asked, okay, tell me about the charge. Okay, same type of thing. All right. So even before we start doing this, we know we're going to have an electric field going up this direction. But we do want to be able to put it into numbers, to be able to say, here's how big this field is going to be. Okay. Now, is an electric field a scalar or a vector?
I don't know.
Okay. Okay. Does an electric field have a direction? Electric field does have a direction. We just drew it, right? Okay? So if it's got a direction, it is a vector. Okay, which means we need to concern ourselves with which direction it's going. Well, it's going to has parts in the x direction or parts in the y direction. Okay. All right. Now, let me start with Q2. If all we had was Q2, which direction is the electric field? Up. So all in the y direction. We have just Q1. It's in the x and the y. Okay, so we're going to have parts in each direction. And it depends on the angle that it's at here. By the way, again, if we did the geometry associated with this angle right here would be 30 degrees. Okay. So let's go ahead and find our field due to Q2. We'll find our field due to Q1, and then we're going to combine the two. Okay, but we got to combine them as vectors, right? The part in the x direction, the part in the y direction. Okay, so we're in just about Q2. How do we find the electric field? So E equals KQ over E squared. Okay, and I'm going to call it E2. It's the electric field due to 2. So go ahead and put the values in. Solve for E2. Yeah, because what's the units for the electric field? In newtons is in meters, yes.